Welcome to Module 2 on Washington State's I-5 US 12 bridge at Grand Mound Precast Substructure. We're pleased to welcome our speakers, Amy Leland, State Bridge Design Engineer in the Bridge and Structures Office at the Washington State Department of Transportation, Bijan Khaleghi, Principal Structural Engineer with TranTech Engineering, and Associate Research Professor and Director of Implementation with the ABC-UTC, and Nikzad, Principal Engineer with TranTech Engineering. Amy?
Thank you, Mary Lou. As Mary Lou mentioned, this is we're going to be discussing Washington State's I-5 US 12 bridge at Grand Mound, the precast substructure. Most of this presentation is going to be done by Kash and Bijan. I just wanted to thank them for putting this together, but we wanted to give Washington State's thought on it too. So first, let's look at the location. This bridge is located in Washington State. In particular, it is in Western Washington. And if you look at the lower right side, you can see the intersection of I-5 and US 12. I-5 is a major north-south thoroughway in Washington State. And in Western Washington, we have high seismic region. This module is a technical resource that provides background information on the use of a precast vent system for use in high seismic regions. The system is designed for and intended to be used with pre-stressed girder bridges that are built intricately with the supporting intermediate piers. The precast vent system uses precast columns with cast-in-place foundations, precast pier cap beams, and a cast-in-place upper stage pier cap beam. So this module provides information on the system concept as well as the background physical testing for the grouted duct connections and the socket type connection. You can see the outline of our discussion below. So the first thing we're going to talk about is a little bit of introduction and some of Washington State's use of ABC. So this project, the Grand Mound project, is a Highway for Life demonstration project. The purpose of the Highways for Life was to advance longer lasting highway infrastructure using innovations to accomplish the fast construction of efficient and safe highways and bridges. And there are three main goals of Highways for Life: was to improve the safety during and after construction, reduce congestion caused by construction, and three, to improve the quality of the highway infrastructure. As I mentioned, our project is located in Western Washington, which is high seismic. So it has a precast vent system that's used for high seismic regions. We have a socket connection at the column to face and grouted ducts at the columns and column to cap beam connection. All of our connections are designed to be capacity protected, which is typical in our seismic design. And the lower column socket connection has been configured that can be used with spread footings or with shafts. So Washington State utilizes ABC when appropriate, and we actually have a chapter in our bridge design manual where we discuss ABC. So ABC uses different methods of project delivery and construction, and so we have utilized a variety of different aspects. And so this slide right here is just showing you a couple of our examples. We have some lateral sliding projects, precast crossbeam projects, precast columns, self-propelled modular transporter, and other precast elements. So with the ever-increasing demand on the transportation infrastructure and the number of bridges that are approaching the end of their service lives, the need for ABC becomes more apparent. Here's some photographs showing some of our ABC projects. On the left side is our Skagit River Bridge. The bridge itself, one of the spans that collapsed about 10 years ago, and we had to replace it, and we used a lateral slide system in order to replace it. The upper right is also a lateral slide. The lower bottom shows precast columns, and in the lower right, we have our Minette Bridge, which uses a spliced girder system. Sometimes with our accelerated bridge construction, we also need to fabricate off-site and transport to the bridge project location, such as the case for the upper photographs. At the Hood Canal, what we have is the truss system. It was fabricated off-site and then transported along the coast to the project location. On the lower left, you can see Alaska Way Tunnel. What this is showing is that we used a lot of precast decking within the tunnel itself to help accelerate the project. On the lower right is our SPMTs at the Lewis and Clark Bridge, where we replaced the deck itself, and deck panels were replaced nightly, and during the day it was opened up to traffic. So every night we close it down and we replace a panel or few panels, and then we open it back up. So those are just some of the examples that we have utilized in Washington State. Now to go further in depth on this project, I'm going to turn it over to Bijan.
Thank you, Amy, for the introduction and good presentation. So I continue Amy's presentation with focusing on design and detailing requirement for the bridge, especially focus on the seismic design as well. So seismic is a requirement for bridges in Western Washington, and we do have some challenges in Western Washington. We are dealing with the Cascadia subduction zone, M9 long duration earthquake, and also basin effect and liquefaction, as well as the lifeline consideration. That's something new that we want to have bridges that survive after have some level of functionality and serviceability after the earthquake. So the picture over there on the lower left shows the basin effect that's being studied by the University of Washington, and on the right side is the subduction zone that we have. So that the picture is showing the bridge collapses due to the seismic event. These are not in Washington, but that shows obviously why we need to design bridges for seismic. So the design specification used for ABC, for bridge design and ABC is actually LRFD bridge design specification. This is the basic code for any bridge design. And then in particular in Washington State, we use the guidance specification for seismic design, which is a displacement-based design. And also recently is available the guidance specification for ABC. That's Mike Pulmo's masterpiece adopted by AASHTO, and he covered that in the previous presentation. The balancing the stiffness is a requirement by WSDOT. It's recommended by the guidance spec, but requirement in WSDOT, and that gives us a better distribution of lateral forces due to seismic event in substructure members within the pier, between the columns, and as well as for the longer bridges, there is adjacent frame. So some harmony on distribution of the loads and behavior of the bridge during the seismic motion. So the focus of design is using the type 1 ductile substructure with essentially elastic superstructure. So we are going to talk about the specific bridge, that's a Maton bridge, but this is a precast element, but once everything put together, it's going to act emulative, similar to cast in place, that meet the type 1 requirements of the AASHTO LRFD specification, and going to ductility of 5 or 6, depending to single column or multiple column bend that we have. So once we do assign the plastic hinging in top and bottom of the column based on the ductility requirement, then member adjacent to the plastic hinging as required by the guidance specification should remain elastic. And in order to do that, there is a principal stresses that need to be checked, and the limits for principal stresses are provided here. And since we are also going to a larger ductility, so we want to also make sure that the bridge is under control in terms of P delta effect. So the guidance specification provides the limitation on P delta effect for type 1 structure up to 0.25 MP, that the P delta effect that should be considered. AASHTO guidance specification is also very specific to amount of rebar that we need in the joint in order to meet the capacity protection of the joint. So these are the area that we do have plastic hinging, but we want to preserve the upper and lower portion of the column, top and below of plastic hinge as capacity protected, and these are the principal stresses that need to be checked during the design. In particular, in Washington State, there are two levels of design for that, and this level is safety evaluation earthquake, SEE, which is 7% probability in 75 years. This is required by the actual guide specification, and also functional evaluation earthquake. So the level of functionality that is expected after the earthquake, that's a lower demand, is a 30% probability, exceeding in 75 years is a 210 years return period. So with that, we do have, in order to meet the requirement for that and the ductility that's required for the bridge. So we do have a ductility assignment for bridge, for different component of the bridge based on either the bridge is a recovery bridge, a critical bridge, or ordinary bridge, as mentioned earlier as a lifeline designation. So this particular module is focusing on the Washington I-5 US 12 bridge at Grand Mound Substructure. This was a bridge that was the owner was Washington State Department of Transportation, and engineers from Washington State. Tri-State Construction was the contractor. Precast concrete was by Concrete Tech, and also research by University of Washington, that we're going to talk about a little bit of all of this. So what is important in seismic design in accelerated bridge design in seismic region is we want to meet this accelerated bridge design, we want to meet the seismic design requirement, and we want to also meet the performance requirement, something that meet the AASHTO 75 years design life or 100-year service life. So putting all this together, we got to have a seismic analysis and design, cumulative design. These are, as you can see, the point of maximum moment and shear are the connection, and this is the connection where you put all this, bring these precast members together. So these are the focus of this presentation, the connection, how to build that act as cumulative to CIP concrete. Energy dissipation and capacity protection, there's a ductility requirement. Load path on the reversal load, development of cyclic inelastic deformation, joint proportioning for SCC C and D, and long-term performance and longevity and constructability, which is a very important. We want to have something that's constructible and could be used over and over. These are the designing seismic design requirement steps that we used. The site class C that was assigned to this project. The design procedure based on the guidance specification. We use the type 1 substructure, which is a ductile substructure and elastic superstructure. Perform demand analysis, design and check the earthquake resisting element, ductility requirement, and also in that case, we are having the pocket and socket connection. Grouted duct and socket connection is not the pocket connection. And also capacity protect the remaining element that I mentioned earlier. In this case, we had a spread footing at the bottom and cap beam on the top. So one of the features of this bridge was this precast, entirely precast bend system and superstructure. Precast column was done in 3 pieces, and we did have a precast bend cap. The lower portion was precast, and then that provided the base to set the girders, precast girders on top of that, and then only the upper portion of this one is cast in place, and this cast in place was in order to bring the column and the beams and the lower cross beam together in order to get a moment resisting the connection for the bridge. So this is what we have: 2-stage design. A stage 1 bend cap design, which is a lower bend cap. That one is a precast pretension member, 53-foot long pieces attached together. Then we check pressure capacity and shear pressure capacity due to the weight of the concrete and girders when we put on top of that. And once that then cast concrete, we go to a stage 2. This is the superimposed dead load and live load, and the seismic displacement demand and capacity, and check flexural and shear capacity. That's among all the other things that we need to do. So as focusing on the connection again, so that's a grouted duct connection. The precast column bar is going through the precast bend, and actually requires that it goes all the way to the top, to the bottom of the slab rebar in order to engage the diaphragm entire bend in the seismic motion when we develop plastic hinging in this zone. So this is very important. These bars could be developed within the length of the grouted duct, but the actual requirement that we extend it all the way to the top of the gate. So once during design, we did have the pushover analysis for transverse and longitudinal direction to ensure the displacement demand and versus displacement capacity, so to ensure that we are meeting the lateral movement within the acceptable range and the capacity of the structure. We also used the strut and tie model for this project. That was a Highways for Life project, so we did have some additional design requirement by the university and by the consultant work on that one. So on the superstructure portion, column to cap connection is the strut and tie model. As you can see, is one integral joint that was used for the strut and tie model. And then the other one with the socket connection of the column into the cast in place footing. And that one, as was mentioned in previous presentation by Mike, the column bar were extended below the bottom mat, and then that engaging the entire footing in the seismic movement. That seismic movement is coming the lateral load, so the strut will be developed through the column plastic hinging to the bottom of the footing, engaging the entire footing. So the grouted duct connection was previously also tested and researched at the University of Washington, and this is the outcome of the research, and that for all bars sizes that could be developed within a shorter distance into the grouted duct, and that's because the strut action that we are getting when we doing the pull-out test. So this is as part of the Washington BDM for grouted duct. This was essentially used, and the connection between the columns, because the column was in segment, and with grouted duct connection. The connection, the grouted duct connection was tested at the university to meet the seismic demand requirement. We went to the ductility ratio, the drift ratio of 5.2. That's way above that what we expect during the seismic, and we go to that level of ductility without any loss of capacity, which is that desired thing. And this is the equation for bar development length into the grouted duct. So in Washington State, majority of bridges are single column, single shaft, although the Highways for Life project was a single column on a spread footing. So that one was tested as part of the project, but we also did tested the column to shaft connection to ensure in that case the socket connection that work, and we are capable in both cases to develop plastic hinging at the bottom of the column. And these are the tests that was done to ensure that seismic behavior. For the socket connection, there are a couple of options. That's wet cast in place. This is the one that we used. The column was precast, and then the CIP footing was cast around that. And then the other option is the form precast if you want to do the socket connection upward and so on. So these are some of the detail on that one. Again, you have the precast column that's coming down there. We have the footing reinforcement. The advantage of this detail that the force transfer between the column to footing is through the interface shear between the column and the surrounding concrete, is not through the bar going through the column. There is no bar going through the column, and everything was taken care of. That has a huge advantage in ABC, so you don't worry about having hole into the precast elements and so on. So here explain that the sawtooth connection that we did have in order to get the interface shear requirement. Again, here you can see the column bar to the bottom of the lower mat footing, and here you can see the column section is transformed to octagonal shape section at the interface, so that's allows to better uniform behavior of the column under the seismic load. And also we're providing the rebar on either side, so to ensure that the performance of the structure. The development length for the column into the bend cap was also based on the interface shear requirement, cohesion, friction, and K1 and K2 factor, and something slightly greater than DC. The depth of the footing cover the development required. So that's what this detail is about. So the same study, we did the testing for the precast column to shaft connection, and that's the equation that required the development length that required in order to ensure that. That detail also has the different bar concentration requirement, as the demand is high at the plastic hinging, so we do have the portion of that is require more confinement reinforcement spirals than the lower portion of that. So the same concept could also be used for CFD, concrete filler steel tube, column to cap or column to footing connection, and these are the equations that's adopted by Bosch.PDM for this kind of application. So with that, I pass to Nikzad. Kash is going to talk about the fabrication and construction. He also continue with the lessons learned and conclusion. Kash, the floor is yours.
Thank you, Bijan. Again, this section will go through the actual application of the research that was done, that was described by Bijan. We go through, all the construction, starting from footing all the way up to the bend cap connection and the connections of the column to both the footing and the cap. This slide shows the construction sequence. You have seen this slide before through Mike and Bijan's slides, and basically shows the two-stage cap construction here. The first phase of the cap is precast, and the second phase is cast in place, and basically it incorporates the precast girders into a continuous structure. These are the quantities of the precast elements that was used for the Grand Mound intersection at I-5 for US 12. Again, I'm not going to go over this slide. It's basically the same slide. It's just the theory for having a plastic, hinging occurring in the column. Basically, the idea of weak column, strong superstructure and substructure to keep it elastic. This slide shows the the bottom segment of the precast column. Again, these columns for this application were fabricated in 3 components, 3 segments, to basically illustrate the segmentability of you can do segmentability on these columns, especially for long column applications. The elements are kind of small, but we wanted to provide the example there. You can see the octagonal part of the bottom section of the column, and the rebars that are coming out in order to go into the middle portion. And also the right picture shows the fabrication of this bottom segment. These 2 pictures show the top column segment and the middle column segment. You can see the dots here, and basically, how these components get incorporated into each other. As mentioned by Bijan, these segments were fabricated at Concrete Technology in Tacoma, and they were transported to somewhere in central Washington at the job site. The components were from 18 kips to 25 kips each. Not very heavy, not very long, but again, the application was to demonstrate it for a wide variety of segments that we can transport. On the bottom, this slide shows the erection of the bottom segment of the precast column. The segments are 25 kips each, and as you can see, the rebar formed on the lower left picture for the cast-in-place footing, and there is a leveling pad there that is basically sitting below the bottom mat of the footing. On the right hand side, you can see some leveling shims, and basically the bottom segment is being lowered into the footing. This slide shows the concreting activities after the bottom segment is lowered. The concrete is poured around the bottom segment, and you folks saw the reinforcement around it, both by Mike and Bijan, and the foundations are backfilled after that. Footings, in this case, shallow footings. This slide shows the different segments are being erected. It's a 3-piece precast column with intermittent joints. You can see also the shims for leveling the components together. And the right picture shows the completed 3-segmented precast column with its intermittent joints. Again, this slide shows the erection of the columns and the completed columns at the end. The columns were braced in order to keep their stability and for grouting purposes. In this case, since the components were kind of small, it was ensured that the grouting wouldn't lift this smaller components, off of their position. This slide shows the erection of the precast cap beam. The cap beam was fabricated in 2 segments. The out-to-out width of the bridge was 84 feet, and as you can see, the length was an issue, and the weight for transportation. Hence, the cap beam, the pre-stressed precast cap beam, was fabricated in 2 segments, and this slide shows that. The bottom lower picture shows the closure pore between the two segments, and you can see the some congestion in the reinforcement in the closure pore, and we'll get into that into some other descriptions on that on the closure pore on the next slide. This is a better picture of the closure pore, and you can see the congestion in here. Originally, the shear stirrups for the closure pore were specified as closed hoops, but the contractor soon realized that that's going to be a challenging task. Hence, the shear stirrups were the closed hoops were redesigned into three basically shear ties to make a hoop out of them, and that was the way that the closure pore shear reinforcement was constructed. And the closure pore width is 5.5 feet long for this application. In order to ensure that the contractor can perform the important, grouting of the ducts, specifications were written that the contractor should do a test, especially for the important lap splices, a mock-up test of the grouted joint. And the contractor did perform that test successfully, and then later on, went on with grouting of the lap splices and the ducts for the column and the capping. This slide shows the grouting activities. Basically, the form works were prepared around the joints, and the ports were provided. The grouting ports, and after that, the grout was pumped into the ports all the way up to the first phase of the precast cap beam at the top. In this case, if there were any ports that were not, later on, the ducts were inspected to see if there were any issues with the grouting. And then they were repaired, and the grouting was repaired on it. Next slide, please. So this slide shows the grouting joints, the sequence of that, installing the forms and sealing them well, pumping grout into the ports, and basically the port goes all the way to the first phase of the precast cap, and then removing the forms and inspecting the grout tubes after that. And we mentioned that on the last slide. After the precast bent was completed, the substructure is done, and the superstructure was construction activities ensued, and basically the precast girders, the deck bulb T girders, goes on oak blocks, and basically the welded ties between the girders, casting the intermediate diaphragms, and basically the feeder diaphragm gets casted later after slab casting. This is a standard washed out procedure to basically balance the flexural stresses, the positive and negative, and then at the end, the traffic barrier and sidewalks were cast in place to complete the superstructure. Lessons learned and concluding remarks out of this experiment. The first prototype bridge that was constructed successfully based on the research. Some of the lessons learned: tolerances of precast pieces were not consistent with survey tolerances. Some of the rebars were not quite centered in the ducts, and pressure from grouting may leave segments, and in this case, the segments were small, but then again, the the demonstration was for ensuring that longer columns can be done in segments. Shim locations and grout lifting pressures need to be included in erection plan calculations. Grout, form work for grouting is crucial, and ability to seal them is key to successful grouting. During inspection and grouting, it would be helpful to grout tubes where as mapped as part of the precast operation. As far as the concluding remarks, the goal of WSDOT Highway for Life project was to basically bring the emerging technology for ABC connections for a two-stage cap beam construction in seismic regions, and this was done successfully throughout this project. And the project provides a successful proof of design and construction of connections of a fully precast bend system meeting seismic design requirements. And it also demonstrates a successful collaboration amongst DOT personnel, contractors, precasters, and researchers, which in this case was University of Washington. Washington State Department of Transportation continues to look for opportunities to apply this technology, the ABC technology, along with other methods for the ABC within the state of Washington. And thank you. We are ready for questions right now.
Thank you, Amy, Bijan, and Kash. We'll now begin the Q&A session. Paul?
Okay, thank you, Mary Lou. We got a few questions. We've got very little time left. I'll try and go through them real quick. Does the column have to be in saturated surface dry condition prior to casting the surrounding concrete for the column footing connection?
I will answer that. Yes, it does. In order to get a good bond between the column and surrounding concrete.
Okay. Here's one that came in during your presentation. It says, at what stage is grout applied to the segments? Slide 45 shows when the top cap is placed before grouting the connections.
Again, on this one, Cash mentioned that the segments are relatively small. So rather than grouting one by one, we erected all the segments and then put the cap, and then we did the grouting in order to prevent the uplift of the section due to the grouting pressure.
Okay. What was the reason for 3-segment columns? It seemed like maybe with the weight you could manage with just 1 or 2 segments.
Yeah, we could do it cast in place also. This was the demonstration project that we were trying to demonstrate that a column could be cast in segment. There are bridges that has a 40-50 foot column, so those are doing one piece for shipping and handling is difficult. So this project demonstrates that we can have column in segments and erect it on the job site and grout it and put it together. That's a good comment.
Okay. I'm going to turn it over to Kathy. We may have another question or so. Kathy?
I have actually just 2 quick questions because we're a little short on time. First of all, does the socket have to be octagonal? Is there a reason for that geometry?
There was a couple of reasons for that. One is that to get the uniform behavior on the seismic, because seismic doesn't follow the axis of the bridge. It could be in any direction, so you get some uniformity. And then the other reason, we are providing the sawtooth for the roughened surface. So that allows to have the, we could have it circular, but having the octagonal allows to have the sawtooth over there to get the interface shear picture.
Right. And then the last question for Amy, actually, the closure pore was really quite large. In the future, might Washington consider using a UHPC closure joint to tighten that up?
We've definitely been doing a lot of research, and there's been a lot of research on UHPC. So that is something to be considered. We have not done it on a crossbeam thus far. Does not mean that we will not. So UHPC is advancing tremendously, and that is something we will be looking for in the future.
Great. Thank you very much. Very Very informative presentation. We'll turn it back over to Mary Lou.
Okay, thank you, Paul and Kathy. We're at the end of the second 40-minute module. Thanks again to Amy, Bijan, and Cash for presenting the second module.